Alright, welcome back, guys. Alright, so we're going to cover 3.6, and this is on basically utilizing a system of equations to solve a problem. Okay, so we'll see some word problems in this section, and we'll have to try to translate what we have, or what we're given in that word problem, into a system of linear equations, and then subsequently solve that system. Alright, and in the process of translating that information into a system of linear equations, you need to be on the lookout for a few terms. Okay, so I've got some listed here in this chart. Yeah, so if you look here, it says many times we're interested in representing a scenario mathematically. And for this, we're going to utilize variables, okay, of course, for the unknowns, numbers, and then mathematical operators. Okay, so the variable, like I said, is going to represent the missing information. And then we'll need to try to translate. We'll be given information verbally, okay, or in other words, in written form. And we'll have to translate that to mathematical statements. Alright, so some words that connote addition are going to be add, sum, S-U-M, plus, total, increased by, more than. All of these are going to connote or indicate that we use the addition operator. And then words or phrases that will connote subtraction are going to be subtract, obviously. The difference, okay, so for example, if I say, what's the difference between 40 and 30? That means you're subtracting 30 from 40. And the difference would be 10. Minus, decreased by, if something is decreased by something else. Less than, of course. And then to denote multiplication, multiply, of course, product. So if I say the product of 2 and 3, that means I'm multiplying 2 by 3. Times, twice. Twice means we're multiplying by the number 2. And then the word of. Okay, sometimes when we're using percentages. And then for division, guys, it's divide, quotient, divided by ratio, and per. Usually quotient's the one you're going to see the most. And then finally, the word is always used to represent equality. Okay, so if I say 5 times some number is 30, that means 5 times that unknown number x is equal to 30. Okay, so you can translate that verbal phrase into a mathematical equation or mathematical expression or statement. And that's what we're going to get some practice with first. Okay, so in your homework, you may initially start out with just simply getting practice translating verbal statements to mathematical statements, okay, or even equations. You may not necessarily be trying to solve those equations, just the process of translating, okay. And then toward the end of at least 3.6, you'll be actually trying to solve that system of equations. Alright, so let's look at example 1 here. The translation of the statement, the sum of 3 numbers is 60, is, so in other words, we need to translate this verbal phrase, the sum of 3 numbers is 60, into a mathematical, algebraically, in other words. Okay. Well, the sum connotes addition, so we know we're going to be adding. We see the word is in here, so that means we're going to be using that equal to operator. And then 60, okay? The issue is we don't we don't know what those three numbers are, so we're going to utilize or employ three different variables. And usually the homework will tell you which variables to use, okay, but I'm just going to arbitrarily choose x, y, and z. So if we're talking about the sum of those three numbers, then I would be adding those three numbers. Well, I don't know what those three numbers are, so I'm using variables. So x plus y plus z is, okay, in other words, has to equal 60. Okay, so I've just translated that phrase into a mathematical statement. Okay, now notice there's nothing to solve. It didn't ask me to solve anything. It just simply said to translate this. Alright, let's look at example 2. We want to translate this statement. The first number is 60 less than the sum of the other two numbers. Okay. Well, we're talking about three different numbers here. The first number and then two other numbers. So we don't know what those numbers are. So I can say I'll let x represent my first number. And then I see the word is. So that indicates that I'm going to employ the equal to operator. So x, or the first number, is, and then it says 60 less than the sum of the other two numbers. Okay. So what's happening here is I'm going to be taking 60 away from the sum of these other two numbers. Well, this is sort of like the order of operations. I need to first figure out what the sum, how to represent the sum of these other two numbers. Well, these other two numbers I can represent with y and z, and their sum would be adding them together. Okay. So this represents the sum of these other two numbers, y plus z. But 60 less than that means I need to take 60 away from this sum. Okay, so you can keep this sum in parentheses if you want, to treat it like it's a unit, and then you can take 60 away from it. Okay, it's not the other way around. Sometimes students want to write 60 minus and then the sum of these two numbers. It's 60 less than this sum, so you're taking the 60 away or subtracting it. And that, guys, is our mathematical equation in this case. Okay. Now, if the equal sign is, or excuse me, if the word is not in your phrase, then you're not going to be using the equal sign. Okay, because I know probably in maybe some of the support homework, you'll just simply be converting these phrases into expressions, not actual equations. But this would be it. And you can see here, once I put this together, I don't have to keep the parentheses anymore. I just utilized the parentheses here to kind of show me that I was treating this sum of these two other numbers as one unit right here, from which I would then subtract 60. Okay, so this would be it. Alright, okay, so now you'll get some more practice when you watch that support video for 3 points. Oh, well, I guess, yeah, you guys won't actually be watching it. Okay, this video is strictly for 3.6, or strictly for college algebra, not college algebra with support. So anyway. Alright, well, let's continue. Now what we're going to do is we're going to look at, we'll be given a word problem like this, and so we'll convert the information that's given in this word problem into equations, okay, just like I did here. And then we're going to go a step beyond that. We're actually going to solve that system of equations. And we're going to be able to get 3 equations out of these problems, okay? Alright, and of course, when it comes time to solve that system of linear equations, we're going to be using the elimination method, okay? So I just put those same steps in here. I'm not going to go over those again. But let's look at this first one, example 3. Alright, so it says Kim is designing a triangular shaped pendant for a client of her custom jewelry business. And this brings to mind that many times, guys, when you're trying to solve or work out these word problems, if having a picture is pertinent, then I would draw myself a picture. That can help a lot, help you visualize kind of what's going on here and help you be better able to set up those equations. Because I think the most difficult part or the most challenging part of these word problems is actually setting up the system. Once you get the system set up, you can typically solve it. Alright, so we've got this triangle basically, okay, and I'm actually going to draw a triangle for you to kind of illustrate this process. So here's my triangle, and it says that the largest angle of the triangle is 70 degrees greater than the smallest angle. Okay, so from this statement right here, we can come up with an equation. Now what you're also going to need to, well, let's read the rest of this first. It says, it then goes on to say the largest angle is twice as large as the remaining angle. Okay, so this remaining angle is, it's not the largest and it's not the smallest, so it's kind of the one in the middle. And then we want to find the measure of each angle. Okay, well, how do we do that? Well, we set up a system of equations that models what's happening here, and we solve that system of equations. But we're going to have to use some variables, okay? So the first step is we need to define some variables. We have three unknowns. We're trying to find the angles of this triangle, okay? And a triangle has three angles. So I'm just going to arbitrarily choose to let x be the largest angle, okay? And that little symbol right here, by the way, guys, represents an angle. So x is my largest angle. I'm going to arbitrarily choose to let y represent the measurement of my middle angle. And then I'll let z represent the measurement of my smallest angle. Okay. And now once I have my variables defined, now I can start trying to construct my equations. Alright, so let's look at this second sentence. It says the largest angle, which is x, is 70 degrees greater than the smallest angle. So if I translate this, I'm going to say x is, so x equals, or in other words, my largest angle is, or equals, 70 degrees more than the smallest angle. That's what this is telling us right here. Okay, so I can write this, my smallest angle is z, so I can write z plus 70. Okay, or you could write 70 plus z. The order doesn't matter. What's important here is that your largest angle is equal to 70 degrees more than your smallest angle. Okay, or in other words, you would have to add 70 to your smallest angle to get it to equal the measurement of your largest angle. So that's my first equation. Now I'm going to look at this other sentence. Here it says the largest angle is, again, twice as large as the remaining angle. Okay, so the largest angle, again, is x, is, so equals x. The largest angle is equal to twice as large as the remaining angle. Well, what does twice as large mean? That means whatever that remaining angle is, if you double it or multiply it by 2, okay, it'll be equal to x, or the largest angle. So in other words, x is equal to 2 times y, because y represents the remaining angle, or the middle angle. Alright, so that information allowed me to come up with two equations. But I've got three different variables here that I'm trying to determine the values for. So I need a third equation. I cannot have three variables with just two equations. I always need a third. And the third, guys, isn't explicitly, the information to construct the third equation is not explicitly given to you here. It comes from a property of a triangle. And that is that a triangle, if you add all the angles together in a triangle, it has to equal 180 degrees. Okay, that's a property of a triangle. If you were to add all the angles of a square, that would equal 360 degrees. If you had a pentagon, or in other words, a geometric figure with 5 sides, it would be 540 degrees. Basically, the way it works is you keep adding 180, 180, 180, 180 each time you add a side to the geometric figure. Okay. So anyway, knowing this, I can construct a third equation. That means that if I add my largest angle to my middle angle to my smallest angle, that has to equal 180 degrees. Okay. In other words, x plus y plus z equals 180. And guys, this brings up something. Typically, in all of these problems, you will always have an equation that looks like this, in which your first variable plus your second variable plus your third variable equals sum total. Okay? And then you'll have two other equations here. Alright, so here is my system. Now, what's different about this one than the systems that we saw in 3.5? Well, for one, there's a couple things. For one thing, all of my variables, they're not on the left-hand side. So I'm going to have to move some variables around. Furthermore, in each of these equations, I don't have every single variable. Sometimes I'm missing. See, this one has an x, z, but it's missing a y. This one has an x and a y, and it's missing the z. Okay, so my first step is to get my variables on the left-hand side, my constants on the right. So guys, you can do this simply by moving these terms over and changing their signs. So if I do that, I'll move the z over here, and I'll make it a negative. All right, so I'm going to rewrite these out over here. So for my second equation, I'm going to put the x where I already, in this first column, where I already have an x. And then when I move this z over, it'll become a negative. So I'll put that with the z in that third column, and then this will equal 70. And then over here, I have an x. I'll move the 2y over, but it'll become a negative 2y. Hold on just a minute, guys. People are talking in the phone. Alright. It'll become a negative 2y, and I'll vertically align it with the y that I already have, and then this will equal. You may say, well, what's it going to equal? I just moved it over. There's nothing left. Well, if there's nothing left, then it equals 0. Okay. Alright, so now I have this in standard form. So now I can go about solving this system. Okay. And let's see. Let me make sure. Okay, well, I'm just going to leave it like this. And I'll go ahead and label my equations. I'm going to label them on the right-hand side. Okay. Now you could choose to eliminate x if you want. But guys, whenever you have equations that are missing terms, it actually allows you to solve these systems a lot quicker, because you can eliminate a variable in a single step. Instead of having to combine equations 1 and 2 and then 1 and 3 just to eliminate x, the way we did in 3.5, I can choose to eliminate another variable, let's say z, simply by combining equations 1 and 2. And the reason is because equation 3 doesn't have that variable. Okay, so you'll be able to solve these a little quicker. And that's exactly what I'm going to do. I'm going to combine equations 1 and 2. I'm going to rewrite them over here. I'll just put it right here, I guess. And I'm going to try to eliminate my z's. Okay, I notice that they're already opposites, so I don't need to multiply one of these equations by a number. I don't need to manipulate either of these. I can simply start adding my columns. X plus x is 2x. The y just falls down, but the z's will be eliminated. The z's will be eliminated. I'll drop them equal sign, and I need to keep that color. And 180 plus 70 is 250, okay? So this would be like my intermediate equation here. Now, the nice thing here is I can now go to combine this one, because it has exactly an x and a y, with my third equation, which has an x and a y, okay? And that's what I'm going to do. So I'm going to take this equation that I've just obtained, rewrite it, and combine it with the third original equation, because it contains exactly an x and a y, and I'll be able to eliminate either x or y, whichever I want. Okay. Oops, I wrote equals twice. Sorry guys if I appear a bit incoherent. I've been sick the past few days. Alright, now I'm looking at this, and I'm noticing that my y's already have opposite signs, but I need the y on top to be 2y. So what I'll do is multiply my top equation by 2, and that will give me 4x plus 2y is equal to 500. 250 times 2 is 500, and then I'll simply recopy my second equation. And now I'm set up to eliminate those y's. And so 4x plus 1x is 5x equals 500 plus 0 is 500. And now I've got this all the way down to x. And I did it a lot faster than I did in 3.5. And so I can divide both sides by 5. And we can get a value for x. We'll get 100 degrees, that is, because x represents the measurement, okay, of this triangle. You've always got to go back and remember what your variables represent. You've got to keep that in mind, guys, because the question may not ask you for the measurement of all three angles. It might ask you for just the middle angle, okay? So if you come up with 100 and think that you're finished, you're not. You've got to figure out the values of these other variables as well and remember what they represent. Alright, so now that I know what x is, I can start my back substitution process and find y and z. Okay. And guys, since these original equations are missing variables, I can use maybe this second one. Okay, I'll start my back substitution. I'm going to use that second one. A lot of this is just arbitrary, okay? I could also have used the third equation, and that would have given me the value of y, okay? So you're going to find that these systems, if you're doing them by hand, there's a lot of freedom here. Alright, so I'm going to plug 100 in for x. Okay, so 100 minus z is equal to 70. Okay, I really don't need that 100 in parentheses. Oops. So if I solve this for z, I'll need to subtract 100 from both sides. And I'll be left with negative z is equal to 70 minus 100 is actually negative 30. And then to isolate for z, if you guys remember, you actually have to divide by negative 1. And so you end up with z is equal to positive 30 degrees. And this makes sense. We want a positive. You always want to ask yourself, guys, are my solutions making sense in the context of this problem? Because if I came up with a negative, that wouldn't make sense. Okay, so now I know the value of my smallest angle. It's 30 degrees. Okay, and so now I've got a lot of freedom in solving for y. I can use really any equation here. Okay, but I'll just choose number 1. X plus y plus c equals 180. And I'll put it over here. Okay, because I know what x and z are. X is 100. Z is 30 degrees. Okay. This one you might could even do in your head. 100 plus 30 is 130. We have 130 plus y is equal to 180. Whoops, getting ahead of myself there. Here I would need to subtract 130 from both sides of the equation. And this would give me a value of 50 degrees for y. Okay. So my last step here, guys, is to restate what I found. X, which represents the largest angle, is 100 degrees. Y, which represents the remaining angle, or the middle angle, is 50 degrees. And then finally, Z, which represented the smallest angle, is 30 degrees. Okay? And so we have found the measurements of the angle of the angles of this triangular shaped pendant here. Okay, so you've got a problem very similar to this. Okay? In your homework. And also, if they ask you for those angles, you know, sometimes I think they ask you for the angles separately, independently. Okay. But anyway, all right, we're approaching 30 minutes, guys. So I think I'm going to stop the video here, and we're going to see one other example in the part 2 video. Okay, example 4. This one, in many ways, is just like this last one. All right, so I'll see you then.